Katrina, hear me?
डबल यूएसबी पोर्ट आहे
नाही भरलेलेच आहे.
तुमचं लॅपटॉप लावायचं तिथे
हा
हा लॅपटॉप लावायचं
हा कशाला?
सेम लॉगिन आहे ना
हा
प्रेझेंटेशन यातच एक यात नाही असं काय आहे का
हे प्रेझेंटेशन करणार.
यातनं करू शकतो ना प्रेझेंटेशन
हा
केलं का ते जाऊन मी ठीक झालं
नाही तिथे काय इथंच करा ना दादा, इथंच करा हो.
वॉट पण चालणार
अरे तो आयर वर्क करत नाही त्याच्यावरच नाही काय आयर वर्क करणार नाही त्याचं लाईट चेंज काम करणार बस तिकडून लाव.
नाही झाले
कॅमेरा आता कॅमेरा गेला.
यूएसबी ठिकत नाहीये
हो तसं जमल ना.
काय काय
मीटिंग एंड करून डबल जॉईन केली तर ट्राय तर करा तिथून लिव्ह करून.
Hi, Jion. Can you please confirm if you are able to hear me from this?
Yeah.
Okay. Hi, Jion. Can you please share your screen and start the presentation? We will try to see if we are able to hear you.
Hello, can you hear me?
We need to do some sound check here first.
Hello, can you hear me?
Yes, you are audible.
Oh, great. I can try to share my screen.
We can start, please.
Okay, I guys see my screen. I can see my screen. So should I start now?
Yeah, we can see your screen. Can you just go ahead with the presentation whenever you're ready?
Oh, yeah, sure. Hi, everyone. My name is John. Today, I'm going to present our recent work on formally certified approximate model counting. So this is a joint work with Yongkan, Mate, Magnus, and Kuldeep. And we are from Institute for Infocom Research, ISTAR, National University of Singapore, Chalmers University of Technology, and University of Toronto. And this work has been published in CAF this year. So let's first start with the motivation. So approximate model counting is a task of estimating the number of solutions to a Boolean formula. It has found applications in many domains, such as quantitative information flow analysis, software reliability analysis, and verification of binary network, and discrete integration, and probability reasoning. So in this talk, we are going to focus on the state-of-art approximate model counting algorithm, ApproxMC, proposed in 2016, and its modern implementation proposed in the later years. And ApproxMC outputs a 1 plus epsilon approximation of the exact model count with probability at least 1 minus delta. So ApproxMC invokes 1 by epsilon squared times log the number of variables times log 1 by delta many calls to an underlying SAT solver. Certifying algorithms produce both an output and a checkable certificate, justifying the correctness of that output. So here we show the outline for a general certifying algorithm. So usually we take the verification problem as an input to an automated reasoning system, and then the system outputs a verification result together with a proof certificate. And later a proof checker takes the original verification problem and proof certificate as input to check the validity of the verification result from an untrusted automated reasoning system. And this pipeline has been widely used in many scenarios such as SAT, 0-1 integer linear programming, SMT, subgraph solving, and constraint programming. In this pipeline, a trusted base is a sound design and correct implementation of proof checkers, and which should be formally verified in proof assistance such as Adbel, Halfor, KickML, Gawk, or Lean. In this work, we are going to come up with a certification of a randomized algorithm, ApproxMC, combine theorem proving and certificate-based approaches. And we are faced with three primary challenges in this work. So first, what does it mean to certify a probabilistic system? So unlike the deterministic system, where for a given input, the output is always fixed. The output of a probabilistic system varies from run to run. So the first question we need to tackle is like, how do we define a certificate for a probabilistic system? So secondly, how do we build a practical, effective proof checker? So usually proof checking is much more expensive than solving. So how do we build an effective implementation to make the proof checking feasible in practice is the second problem we need to solve. So finally, how do we get the formally verified guaranteeing throughout? We need to make sure that the output of our system always satisfies the guaranteeing provided by ApproxMC. And here we show the outline of our approach. We start with a trusted randomness, and that is the trusted random bits to be used by the ApproxMC. And all the statement we made in our method is based on top of this trusted randomness. And untrusted ApproxMC implementation takes this trusted randomness and the input and formula as input. It outputs an approximate model count together with a partial certificate. And later, a verified ApproxMC checker takes this partial certificate as input to check the validity of the approximate count from the untrusted implementation. And during the certificate checking, the ApproxMC checker interacts with a verified CNF XOR unsigned checker. And we name both ApproxMC checker and this unsigned checker together as cert2. It outputs either a certified approximate model count upon success, or it reports an error. And to get a verified ApproxMC checker, we formalize the proof of the probabilistic approximation guaranteeing in Adbel and refine it to a practical certificate checker. On the other hand, the verified CNF XOR unsigned checker is reusable for unsigned proof of any CNF XOR formula. And it supports native CNF XOR reasoning. And we formalize it in Halfor and KickML, which is a verified compiler into the machine level code. And our experimental evaluation shows a low certificate generation overhead. And our tool fully certifies 84.7% of instances within the same resource limits as counters. And we also fixed some minor bugs in our previous pen and paper proofs and our implementations. Now let's look at the approximate model counting formalized in Adbel. ApproxMC provides a probably approximate correct guaranteeing for approximate model counts. So given a CNF formula F, a tolerance parameter epsilon, and the confidence parameter delta, ApproxMC returns an approximate count C such that C is a 1 plus epsilon factor approximation of the exact model count with probability at least 1 minus delta. So here we use SOF to denote all the solutions to the formula F, and we use its cardinality to indicate the model count. So the guaranteeing says that the approximate count C is no less than the model count by 1 plus epsilon and no more than 1 plus epsilon times the model count with probability at least 1 minus delta. And the core intuition behind ApproxMC is as follows. So suppose the plane represents the solution space and every black point indicates a solution. And usually we have a huge number of solutions, so it's impossible to count all the solutions one by one. So instead, we use random XORs to partition the space into roughly equal small cells. So for example, after adding one XOR, we partition the space into 2 parts, which have a similar size. And then we just need to count half of the space and then scale the model count by 2 to approximate the total number of solutions. The XOR constraint is a parity constraint. And for the random XOR, the left-hand side is a random subset of variables, while on the right-hand side is a random bit. And we use random XORs to partition the space into cells because its property ensures that every single cell contains a similar number of solutions. And we conjunct the random XORs with the original formula F, resulting in the CF XOR formula. In most cases, even after we add after one partition, the number of solutions in a single cell is still too large to count them. And then we repeat adding XOR constraints. And after adding each XOR, we partition all the previous cells into 2 subcells. And therefore, we doubled the number of the cells. So after m partitions, we have totally to the power of m cells. And then we continue this partition until a single cell becomes small enough to count. At that time, we exactly count the number of solutions in that single cell using a CF XOR solver to enumerate all the solutions. And we use Cm to denote the number of solutions in that cell. So finally, we return the approximate count C as the multiplication of the total number of the cells to the power of m times the number of solutions in that cell, Cm. And here, the property of the random XOR constraints ensures that each cell contains a similar number of solutions. And so therefore, the C will be a good estimate of the model count. And we may repeat the previous process for several trials and take the median to amplify the success probability to the design value of 1 minus theta here. And the proof primarily consists of the property of this XOR-based Hashi family that we use to partition the solution space, and also some concentration inequalities and the guarantees provided by the median method. Is the entire proof of approximation in Isabelle proof assistant and building on its extensive probability library. So here we show the formalized proof for the high-level guaranteeing the probability approximate correct guarantee, named the approximation sum. So this formalized theorem takes delta epsilon and projected set S as the assumption. So it formalizes algorithm as a probability mass function over the estimated count. And it defines event that the returned count is in the required approximation range interval. And it finally states that the lower bound on this event probability, which is at least 1 minus theta. So in the paper, we use Isabelle's locales to keep the algorithms guarantee generic and applicable to any Boolean theory. So it means that we prove that the approximation algorithm also works for the theory other than the normal set. For example, it also works for the PB constraint. And we use slight variations of the previous pen and paper proof, and we also fix the missing assumption. We contributed various results to Isabelle's archive of formal proofs, which is an open platform maintaining all the existing formalized proofs, and it can be reused by anyone to construct their new proofs. So now the approximation formalization is also available on the archive of formal proofs. So after we formalize the entire proof of approximation in the Isabelle, we derive a verified requirement to search check, which serves as a proof checker for approximation. So recall that earlier we used m random XORs to partition the solution space into 2 to the power of m random small cells, and then we count the exact number of solutions in one of the cells, and finally we use 2 to the power of m times Cm as an estimate of the model count. So following this algorithm, we know that approximation must search for the correct number m of XORs. And it may use various search strategies and implementation optimizations and other heuristics, but search check only needs to check that approximation found the right value of m. And here the key observation for the correct number of the correct right value of m is that each added XOR approximately halves the solution space. And the correct m is, for the first time, the solution count in a single cell falls below a predefined threshold, which means that it's for the first time a single cell becomes small enough to count the number of solutions. And following this observation, we designed the certificate for our method. So here, let's look at an example. Suppose at the top left, we show the input formula, and on the bottom left, we run approximation, and it returns an approximate count of 184. On the right, we present the certificate for this example. So the first important component is the claimed value of M, which is the number of XORs we use to approximate the model count. And in our example, it's 2. We use 2 XORs here. And following that, we record at least threshold many solutions for M-1 XORs. In our example, the threshold is 73. So that's why here we record 73 solutions. So which means M-1 XOR do not partition the space enough, because we can still find at least threshold many solutions. So the cell, a single cell is still too large to count all the solutions, which means if we want to fully partition the space, we need at least M XORs. So on the other hand, we record 51 solutions for M XORs, which is less than the threshold, which means M XOR do partition the space enough such that a single cell is small enough to enumerate all the solutions, which means that we need at most M XORs, because M XOR is enough to fully partition the space. So combining both A and B, we know that the M is the right answer. Now, the only thing left is that we still need an asset proof to show that there are no more solutions left for the M XORs after we remove all these 51 solutions. So we remove every solution by its negation. So this CNF XOR formula should become a set if there is no more solutions left for M XORs. So now let's move to the last part, the implementation and experiments. So earlier we have already showed that we formalize the ProxMC and extract a practical certificate checker from the Adabel. Now the only thing left is to get a verified CNF XOR and set checker to prove that there is no more solutions left after we add the no more for the M XORs. Actually, there are existing CNF XOR and set pipelines with verified proof checkers. For example, we can use CryptoMiniSet with T-Body. Here, CryptoMiniSet is a CNF XOR solver with native support for XOR reasoning, and T-Body can use BDD to output XOR proofs in LRAD format. Alternatively, we can use Miniset solver with an XOR engine and write down the XOR proof in PB format. And also, we can also blast all the XOR constraints into clauses and use Cadical with purely CNF encoding and LRAD proofs. However, none of these methods provided sufficient performance because they all try to use other proof format to compose XOR proofs. In this work, therefore, we design a checking pipeline with a native support for XOR constraint. We implemented CryptoMiniSet with FRAD XOR and set proofs and a dedicated verified checker. So the solver first outputs the FRAD XOR proof, which is a strict extension of the FRAD format with a support for XOR constraint. And then an elaborator turns FRAD XOR proof into the XLRA proof, which is extension of LRA proof with XOR constraints. So finally, a verified XLRA checker checks, validates the final proof, which natively supports the CNF and XOR reasoning, and it is formalized in Haufel and formalized and verified by Haufel and KickML. And after this, we have the complete prototype of our method, and now we can conduct experimental evaluation to evaluate the runtime performance of our method. Let's first look at the certificate generation and checking. We use ApproxMC to denote the unmodified state-of-art approximate model counter. And we use ApproxMC cert to represent our certificate generating version of ApproxMC. The cert check is our certificate checker extracted from the Adabel. And so last one, part 2, is a metric we use, which indicates average runtime. But for the unsolved instances, we count as double time limit. So the following table summarizes the result over a standard suite of counting problems with 1,896 instances within time limit of 5,000 seconds. So from table, we can see the ProxMC search solved a similar number of instances as a ProxMC, and it also achieved a similar partial score as a ProxMC, which means the certificate generation only adds a small amount of overhead. So here the partial means that the certificate does not include the final unsigned for the CNF XOR formula. Now look at the third check. Third check can solve the 1018 instances out of the 1202 instances where a certificate is generated within the time limit. So it shows that the verified proof checking is feasible. It succeeds for 84.7% of instances with an average of 4.6 times runtime compared to solving. So here we want to emphasize that in a SAT computation, we usually provide an order of magnitude more time and memory for the checker compared to a solver because proof checking is more expensive than solving. However, here, third checker still performs well, even though we give the same time and memory limit for our checker to even though here the time limit and time and memory limit of our checker are the same as the counter. We also evaluate the runtime performance for our native CNF XOR and side checking pipeline. So we use Cadical plus LWrite to indicate the Cadical with velocity CNF and LWrite proofs, and Miniset XOR plus PBP to indicate the Miniset with XOR NG and using the PB proof format. And CMS plus T-body is a crypto Miniset with T-body for LWrite proofs. So finally, the CMS plus FRED XOR is our method. It indicates the crypto Miniset with native CNF XOR proofs. So we evaluate all these proof checking pipelines over 1202 instances from the previous slide where a certificate is generated within the 5,000 time limit. And we also set the same time limit to the checking pipelines. The figure on the right presents the number of solved instances as the runtime increases. So here the x-axis indicates the runtime in seconds, while the y-axis indicates the number of solved instances. So a point xy indicates like y instances can be solved within x seconds. So the higher the curve is, the faster the checker is. We can see that there are substantially more instances certified with CMS plus FRED XOR compared to all the other methods. And our method also achieved a lower Pardo score and smaller proof sizes, and you can find more details in our paper. In conclusion, in this work, we propose a formally certified approximate model counter. We formalize the proof of probabilistic approximate guaranteeing in Asbel and refine it to a practical certificate checker. We also develop a reusable and native CNF XOR proof checker formalized in Hoffel and KickML. Experimental evaluation presents a low certificate generation overhead, and our tool fully certifies 84.7% of instances within the same resource limits as counters. And finally, we also fix minor bugs in our previous pen and paper proofs and our implementation. Our tool and formalizations are public available. You can find the links in our paper. And in the future, we plan to support preprocessing and other series such as PBXOR and NF for our certified approximate model counter. And we also work on the certification of other randomized algorithms. So lastly is an advertisement. So my co-author, Yongkan, who just joined the Nanyang Technology University as a faculty. So he has open positions for prospective PhDs or postdocs. Please feel free to contact him if you are interested. And with that, I want to thank all of you for attending my talk. Thank you.
Yeah, hi, Jiyoung. Can you hear us?
Yeah, I can hear.
Okay. So since this is working, let's try this. Okay, sure. So questions?
Yeah.
Unfortunately, there are some technical issues.
Okay. Can you hear me? This is Moshe. Can you hear me?
Yeah, I can hear you.
So why does it matter that K is the first to achieve a small enough cell? Who cares it's the first? If it achieves a small enough cell, that's good enough.
So I mean, who cares why the cell is small enough?
You said that K has to be the first to achieve a small enough cell.
Yeah.
Why is it important?
Because with this condition, we can maximize the confidence in this process. Otherwise, if like suppose if the cell is too small, like with very high probability,
No,
there's
no,
no solution in the
it's
cell.
not this. You have to prove that the cell is the right size. But why does it have to matter that K is the first to achieve it?
It's a first achieved it.
Why does it matter?
So, if I understand question, you're asking why does it matter if it's for the first time this cell is less than threshold, right?
It's for the why does it matter for the first time?
Yeah, because if it's not for the first time, if you further add XOR constraints, the number of solutions in one cell is decreasing, right? So as you add more and more XOR constraints, the number of solutions in one cell finally will approach 0. And if you use like 0 to estimate the total number of solutions, it's going to be 0, right? So only if you stop at the first point, you have a large enough count, and you have kind of a smooth estimate of the approximate count. Am I answering
Not
your
clear
question?
to me. Anyway, I have to leave, so I'll follow up with you by email.
Oh yeah, thanks for the question.
Hi, this is Dror. I have a follow-up question to what Moshe asked.
Yeah, sure.
So there are a version of ApproxMC, if I'm not mistaken, in which you jump the number of constraints that you add, right?
Yes.
How does it work with your work?
It doesn't matter, right? As I'm right down here. So the practical implementation of ApproxMC can use various search strategy and different implementation optimization and other heuristics. But all the thing search check need to check is just to verify that the M is correct. It doesn't matter how do you search for the correct M.
Yes, but you did say that you need to find the first M. So that is also what Moshe was asking, and why basically I am referring, because there are versions in which you find the right M, but it's not the first M.
That's why
you just find a good enough M for you.
In the certificate, we have to prove that this is for the first time a single cell is small enough, right? So we write down when we use M minus 1 XORs, there are at least threshold managed solutions, which means the cell is not small enough. And after that, we use M XORs, the single cell becomes small enough to count all the solutions. We need both of them. M and M minus 1 XORs, there are still many solutions. And for M XORs, also many solutions.
Okay, thank you. I may follow offline. I'll try to catch you offline.
Yeah, thank you. Thanks for the question.
Thank you.
It's a good question. Oh, yeah. Stop sharing.
Thanks a lot for your talk.
Thank you.
Yeah. So, Priyanka, you want to?
Mahi, can you please share your screen?
Yeah.
Thanks, Jian. Thanks a lot.
Can I present in your machine? Can I present it in your machine?
Oh, yeah, sure.
Sure. Okay.
You have to send the...
Yeah. I'm sending it in Slack, okay? Yeah. Present in your machine. Some permission issue. Hello everyone. Can you see my screen?
Yes, the screen is visible.
Okay.
Yeah.
So I am starting then.
Yes, please.
Okay. So the title is XZSP counting with compact encoding,
And I am Mohammedul Kabir from National of Singapore, and it is a joint work with Shupati Chakraborty from IIT Bombay and Kuldeep Ismail from University of Toronto. So it is about our recent ASP counter that actually we present in AAA 24. So
What happened?
hold on. The next. Okay. So before going to the technical description of our ASP counter, I first present what is ASP or answer set programming. So answer set programming is a declarative programming solving paradigm which has its roots in logic programming and non-motor reasoning. And this particular way of solving solving for concept rules, and a rule is a logical relationship having a body and a head. In this particular slide, the body one up, sorry, the B1 up to BK and not of BK plus 1 up to not of BK plus M constitute the body of the rule, and the atom H it consists the head, it comprises the head of the rule. So this rule say that if B1 up to BK is true, and then if B1 up to BK is true, and there is no way to prove BK plus 1 up to BK plus M, then the H will be true or head will be true. So in fact, the rule expresses some implication relationship in ASP. And a ASP program is a set of rules, and each of the model of a ASP program is known as answer set, and it is denoted by S of P. And answer set follows the default negation, which means that everything is false except there are some justification for something to be true. Let's see the example to understand what is justification in the context of ASP. So here we have a toy program consists of 4 rules, and if we try to see which assignments satisfy the program or satisfy 4 rules of the program, the first assignment that assigns A is equal to true, B equal to false, A equal to false, and T equal to false. So this assignment actually satisfies 4 rules, and S is justified by rule R3, because R3 say if not A, then S is true. So S is justified by rule R3. And if we consider another assignment that assign A equal to true, B equal to true, S equal to false, and T equal to false, this assignment also satisfies the 4 rules. But does are A and B justified in the assignment? For this, actually, we have to check the rules where A and B comes. So A comes in rule R1 and B comes in rule R2. So if A and B are justified, then it will be justified by R1 and R2. So R1 say that if B is justified, then A is justified, and R1 say the other way around. So it looks like a chicken and egg situation, like which one will come first. So it looks like a chicken and egg situation, like which one will come first. So these A and B, they actually are not answer set because A and B are not justified under the assignment. So note that both of the assignment are satisfy the program, but one of them is an answer set, but another is not an answer set. So now, what is the main objective of this work? So in this work, we are interested in ASP counting, or we want to find the number of assignments, the number of answer sets of a given program P. So again, if we see the same example P, and if we give the program to some answer set counter will return 1 because there is one answer set. And note that what is the motivation of ASP counting? It has motivation mean how is the application? So it has application in network reliability, probabilistic inference, and some real world problem. Now we will see what is the state of the art of ASP counting. there are several techniques for ASP counting. First of all, enumeration. Enumeration means actually given a program, you will give it to some ASP solver, and ASP solver will enumerate all the answer set one by one. So this idea is good because the ASP solvers are actually very efficient. But for counting, this technique is not ideal. Because if there are many answer sets, then the solver will run out of memory or run out of time after a fixed time. There is another way that actually doing dynamic programming. For dynamic programming, the given ASP program is represented by some tree representation, and over the tree representation, some dynamic algorithm works and counts the number of answer sets. So this idea actually works well, but the problem is that the complexity of dynamic algorithm is double exponential with the tree width. So it is like 2 to the power 2 of k. So it means that except the tree width is very small, this technique does not scale in real world problems. And the final way is invoking some sharp set tool, which means that if we're given with the ASP program, you convert it to some CNF program and run the sharp set tool. So which mean that you have to convert the P to some CNF program, and over the formula F you run some sharp set tool to count the number of answer set. And also make sure that for each of the answer set there is exactly one model, and also the vice versa, so that we are not overcounting or we are not undercounting the number of answer set. Here is the problem, like for some of the program, the one-to-one correspondency actually is easier to achieve. Like it is called the non-cyclic program. Here you can actually compute a CNF encoding that you can count. But for another type of program that is called the cyclic program, here if you want to compute some one-to-one correspondency between answer set and the model, then the encoding becomes so hard for counting actually. Like if you give the encoding to some sharp set tool, then actually they cannot solve most of the cases. So now we will go a bit deep into the technique. Now how we can convert a sharp ASP problem to some CNF problem. So here the curve completion gives some primary translation, and the size of curve completion is linear with respect to the size of the program P. So since it is linear, so it is actually a promise that if we can count the number of answer sets from completion of P, then it will be efficient. But is curve completion enough, or is it is complete for counting? Here is the problem, that the curve completion preserves the answer sets, but it is not the other way around, mainly for cyclic program. So let's see the example, again the same example, to understand what is the problem with cyclic program. So in this graph, actually A and B are dependent on each other, because the rule R1, there is a dependency between A and B, and by rule R2, this is the other way around. So there is a loop, there is a cycle, and note that here A and B are involved in the cycle, but T is not, S is not. Now first compute the comp of P. The comp it is easy to compute the comp of P. The idea is for each of the atom, we'll see all the rules where A comes. Like if A is true, then it will be true by R1, because in R1 there is A, and also it will be true by R4 where there is R. So sorry, here there is A. So for atom A, we'll introduce a two-sided implication that say that if A is true, then either B or T is true. So it is a two-sided implication. We do the similar for B, S, and T. So this conjunction of equivalence, they actually constitute the comp of P. Now again count the models of P, or see which are the models that satisfy comp of P. So again, the same thing, we can see that there are two models that satisfy the comp of P, but as we know that there is only one single answer set. So here actually we have some observation that how we can count. The existing answer set definition says that each of the atom of answer set must be justified. That we see that in the first example, S must be justified, A must be justified, everything must be justified. So at this point, we think, can we relax the condition? Is it possible to relax the justification for a subset of atom? So here our answer is yes. As long as we are using the Kerr completion, then we do not need to worry about justification for non-cyclic atoms. That we can show that by Kerr completion, the non-cyclic atoms are trivially justified. So all we need to show that the cyclic atoms are justified. So we have to make sure that the cyclic atoms are justified, the non-cyclic are trivially justified. Again, we see the same example. So given the program P, the AB cyclic atom and ST non-cyclic atom, and for the given answer set S, the S is justified by R3, and it is actually make sure, or it is satisfied by the comp of P. But if we come to A and B, here A is true because B is true, and B is true, A is true. So this part actually satisfies the completion of P, but it is not an answer set. At this point, actually, Kerr completion gets fooled. So because the Kerr completion has no way to identify whether which is justified or not. So here is the key idea of our ASP counting. In our ASP counting, we are not employing any one-to-one correspondence encoding. Instead, actually, we search over comp of P and justify that each of the cyclic atom we have are justified, because non-cyclic van der Waals is not important. So here is the contribution of our work. So we propose a ASP counter that is similar to Sharpset from high level, and we search over comp of P because it gives us a over approximation, and from comp of P we make sure that each of the cyclic atoms are justified, and for that we employ a linear size Boolean formula. So the copy of P, it is actually linear size, so it's good, and we use unit propagation over copy of P to decide whether a cyclic atom is justified or not. And since we use some Sharpset type counting technique, so we are able to utilize component caching and decomposition, and we can show that with some minimal change we can convert a Sharpset to ASP counter. Is there any questions so far?
No question in the chat.
So now I will talk about how can we justify each of the cyclic atom. So the way is actually we introduce a variable. The name is copy variable for each of the cyclic atom. So for each of the cyclic atom, we introduce a new copy variable x prime, and it will say whether the x is justified or not. So the root idea of justification is if x equal to 0, then it's trivially justified. So in the case, the x prime will be the x prime will be 0. And if x equal to 1 and is justified, then x prime will be 1. So summary is, if x prime has some value, either 0 or 1, then it is justified. Otherwise, it is not justified. We don't know. So for the given program P, we construct a copy program, the copy of P, as follows: that for each of the cyclic atom, we introduce a copy variable that is A prime or B prime, and a implication that is actually A prime implies A. The purpose of this implication is if A is false, then A prime is false. Similarly, B is false, then B prime is false. So this implication actually obey the first rule of the justification. And for S and T, there is no copy, no implication, because we are not worrying about them. And for each of the rule, actually not for each of the rule, for some of the rule, we introduce a copy of the rule. So it means that, let's say we have a rule R1, and R1 say that if B is true, then A will be true. So we can say it as, if B is justified, then by the rule, A will be justified. And similarly, if if A is justified, then B will be justified by rule R2. So here R3, so R3 is not justifying any of the cyclic atom, so there is no corresponding implication for this. And R4, if T is true, then A will be justified. So again another implication. So there are two set of implications, and the copy of P will be the conjunction of both. Now actually we will see what happened for the models with respect to the copy of P. As we see that the completion of P gives a over approximation of all answer set. So there will be some answers, there will be some assignment, there will be answer set, there will be some assignment that will be answer set, and there will be some assignment that will not be answer set. For answer set, each of the cyclic atom will be justified, and for non-answer set, there will be some cyclic atom that are not justified. So from now on, we represent a program P by a tuple of Boolean formula. The tuple is actually a comp of P and copy of P. So the comp is P, copy of P, there actually P is Boolean formula. And we are not assigning the copy variables because the copy variables are, they are not really variable. They looks like a variable. The purpose is to justify something. So for the given program P, we construct the comp of P and copy of P. And for the given assignment that assign is equal to true, it was an answer set. And for this assignment, the A prime unit propagate to 0 and B prime unit propagate to 0. So it means that for this assignment, A and B are justified. Actually, they are trivially justified because they are false or justified. But for the assignment that was not an answer set, the A prime and B prime, they did not unit propagate to anything. So they actually left off in the copy of P after unit propagation. So based on the observation, here is the alternate definition of answer set. So M is an answer set if M satisfies comp of P, and if the unit propagation of copy of P with respect to M is empty. So based on the definition, here is our knowledge compilation for answer set counting. So for a given program P, we compute the tuple F and G, and we assign each of the non-copy variables because copy variables are not assignable. So we assign each of the non-copy variables, and here is the base case. Like if the F is unset, or the comp of P is unset, then it is not an answer set. So return 0. And if some assignment satisfy the comp of P, then it depends on the copy of P whether it is an assignment or not. If the copy of P unit propagate to empty, or it gets empty, then mean that each of the copy variable actually unit propagate, so mean that they are justified. So in the case we return 1, otherwise return 0. So now I will talk about the experimental result. We implement the algorithm inside the existing propositional model counter like GONOC T for sharp-set TD. So, and here is the benchmark set, and our benchmark set comes from the existing benchmark set of ASP counting. There are actually composition problem of Hammond cycle problem, graph reachability, or S, T path problem. So here is the result. The rightmost column is our sharp ASP, and For Hamiltonian second problem and reachability problem, it is able to solve more instances, but for the S, T path problem, actually Klingo outperform. Actually, this problem has some instances, there are a small number of solution. That is actually in the case Klingo can outperform, but we also develop a hybrid solver combining both of them, where actually we see that it solves more instances. But if we see the aggregated result, the number of solved instances is highest for Sharp ASP, and the part2 score that actually mean the average runtime that is lowest for Sharp ASP. So it indicates that it is actually it perform better over state of the art. Now I come to the conclusion. So here we propose a ASP counter that actually counts answer set from some alternate definition of answer set, and it avoid the one-to-one correspondence encoding. Instead actually it use some alternate definition, and finally we use some sharp set like technique for counting. The source code is already available online, so you can just scan this QR code to get access to the code. And thanks for your attention. I am happy to take question.
Yeah.
Mahi, can you hear us now?
Yeah, I can hear you.
So, okay. Is there any question in your end? Question.
I can hear, but there is some echo.
आपला आवाज कमी ठेवायचा तिकडे बोलत
Hello.
मोबाईल कनेक्ट असले तर मोबाईलचं माईक राहू देत हा आवाज तिकडे जाऊन प्रत्येक
The sound from this room is coming instead of the sound from the mic. Sound from this room is coming instead of the sound from the mic.
Is there any question?
Can you hear? Hello, can you hear?
Yeah, I can hear.
How is the answer set different from our personal?
Hello, sorry.
How is answer set programming different from proposition?
So answer set is different from what?
Proposition.
Okay. Is it propositional model or I did not hear properly?
Yeah, so the question is, how is answer set programming different from propositional solving?
Okay, so in propositional solving, you can assign something to true, assign something to false. You do not worry about justification. But in ASP, if you assign something false, okay, no problem. But if you assign something true, you have to show some justification. So that is different from ASP and satisfiability.
Okay, thanks for the answer. Any further questions?
Thanks, Mahi.
discussion. I've never used this kind of form. I guess you have to put it closely to inside your errors, otherwise it will fall down.
No, in the FireMode I saw that there's some permission issue, that I have give some permission. That is why.
Am I audible?
Yes, positive. Can you hear me?
Good.
So how's it going?
Yeah, so Johannes, things are not very perfect here. So like the mic is not working from the room.
For the online.
Oh, okay, but I can hear you. It's like so.
Yeah, so that is for my laptop. It is working fine, but from the rooms, it is not working. I'm not sure how it will go.
Oh yeah, but that's the usual. I mean, so if there are questions from the room, I guess you're anyways there with the presentation. So it's like I don't think that I will have to answer much, right? I will just be listening, I guess, right? Otherwise, I mean, you have to repeat then.
Yeah, so I can ask someone from the room to type maybe.
Yeah, or just repeat then if there's a question, like you just repeat if I can answer it.
Yeah, sure.
If you don't, yeah. But otherwise, since you're doing the presentation, I think there is not much to do from my end, I guess.
Yeah,
Just tell him that workshop is going fine. It's just the online version which is problematic.
Okay, say hi to the others.
Yeah. Sure.
Yeah, I'm just saying that workshop is going fine. It's just the online thing that is not working at this moment. But in person, it was good.
Okay, nice.
I just don't want you to worry. It was just the online thing which is problematic at this moment. But in person, it was good. We had a lot of in-person participants as well.
Okay,
I guess
perfect,
more
nice.
than 20 people were there at some time. More than 20, 25 people were there in present, and
Okay, very
which
good.
I
That sounds
believe
very
is a
good.
success.
That's
So
very good. Yeah.
yeah,
Nice.
it's just that we had this two online talks because of this visa issue. They could not come, and that's where we noticed there was a glitch. The online Jiong and Mahi, they were online and they were not able to hear us. So we could hear them, but they were not able to hear us. So there was an issue with the problem. Like when we wanted to ask questions and all, they were not able to hear us. That was a main problem.
Right. Yeah, but that's not a big thing then. Yeah.
We are trying to resolve that because there is a gap now. It's a coffee break for half an hour. We'll resume in 20 minutes from now. So we are trying to resolve the issue meanwhile and see if we can get that work done as well. Yeah,
nice.
but rest all went fine. So I just wanted to tell you that.
Nice. That sounds very great. Yeah, I saw that you had quite nice talks on the menu for today. So it's like I couldn't join the morning. I was a bit busy with other things, but yeah.
Yeah.
And I didn't know beforehand, so otherwise I would have organized it a bit differently. Yeah.
Sure. So we'll see and we'll keep you updated about how the mic situation is. And otherwise, we are going to ask someone to write the question in the chat and you can answer because we can hear you very well. The entire audience can hear you. It's just that.
Great. Yeah, and anyways, I think Arjit should be able to answer all the questions because, I mean, he's pretty much involved. He will give the presentation. Arjit should know everything. So he will give the presentation anyways, and guess there will not be much that I have to answer, right? It's like just kind of as a backup, I guess. Right.
Yeah, sure. So if wherever we feel like you should answer, so we'll type. Otherwise, I think mic has worked. We are trying to test it now.
Yeah.
If not, otherwise we'll see.
Okay. All right. See
Otherwise,
you.
we'll assign somebody to write the question in the chat, and you can answer if some issues are there. So we'll try to figure it out. No issues.
Okay. Nice. Have a great coffee break. See you later then.
Yeah. I guess just if you can stay for 2-3 minutes more, we are trying to see if it is working fine.
Oh yeah. Sure. No problem.
Hello.
Yes, you're audible.
Hello.
Yes, I can hear you. Yeah, you're coming on great. Oh, I can see the room. It's like that looks good. It's like, yeah, very nice.
You see me?
Awesome. Yes. Thumbs up. There are even 2 cameras. Wow, that's quite a nice equipment.
I guess now everything is resolved, so you should be able to hear the question and answer directly and see.
Okay, amazing. Yeah, the sound is really great now. It's like, yeah.
Okay, so it's still 20 minutes. After that, we'll start again. So there will be one presentation in person first, and then the discussion.
All right. See you later. Bye-bye.
Yeah, so can you just stay online for a couple of seconds? Can you hear us still?
Yeah, sure. Like you're audible. All good.